Well, I think we can get going. Welcome back, everyone. So we're just about to finish chapter 2. Congratulations. There's one more section, section 2.8, but it turns out to be pretty similar to 2.7. So that's got that going for it. It's kind of a review as well. And the reason I mentioned that is chapter 2 is hard. That's not something I wanted to say right away on day one because I don't want to psych people out, but in a Calculus 1 class, chapter 2 starts out pretty weird. And then it gets much easier once you're in chapter 3. We're going to be calculating derivatives strictly using the definition. And there's a lot of algebra that goes into that. The idea is, one moment, we have an open mic. I'm just going to mute that for you, Craig. But if we have a derivative that we calculate in chapter 3, it's always important to know what did it mean or what is the value of that? What's it saying geometrically? That's kind of the purpose of chapter 2. It's the purpose of section 2.7 and 2.8. So just for the meantime, we're going to calculate derivatives through the definition for full credit on assignments. There might be an exam problem that says calculate the derivative using the definition of the derivative. And so that we'll have to use the limit definition as well. But after we get through here, it all gets a lot easier. So think of this as kind of the hump we're getting over. Also, once we get through this section, we'll have an immediate holiday already on Monday for Labor Day holiday. So we'll just be meeting on Wednesday, Thursday of next week. Well, any questions at all, folks, before we get started then? Okay, so back to section 2.7. Let's take a look at what we're getting into right away. We have this interesting definition right here. Notice it involves a limit where h tends towards 0, and something weird that sometimes you calculate this like in a college algebra class, and they call it a difference quotient, but there's a limit tacked right into it. Also in front of it is m, which is suggestive. It might mean that we're dealing with a slope. And so what we're really doing is going all the way back to day 1 when we were looking at slopes of tangent lines. It says the tangent line to the curve, y equals f of x, at a point a, f of a, is the line through P. Oh, I think I'm missing something there. Sorry for this typo. That point should have been labeled as P for that to be a sensible statement. Is a line through the point P, A, F of A, with that slope, provided the limit there actually exists. So let's draw this out one more time, just to once again get an intuitive feel for how that definition works. So I'll draw just a really fast curve. I need a point A, F of A. So let's put maybe A right here. The curve then can go up and around in this kind of way. Nothing too fancy. We'll just tie it off like that. So it has a finite domain. Here's the function y equals f of x. And the tangent line itself is going to occur right at this point, label up P, A, F of A. So A is the first coordinate, F of A is right here at the second coordinate. And this is our tangent line. I just want to make sure I can draw that decently. So let me zoom in for the moment. When I'm really, really close to A for the first coordinate, the line is going to be very, very close to the curve. It'll be the best local linear approximation. And so drawing that out, I think it would look about like that. So this is our tangent line. Equation of that line, well, if we use slope-intercept form, would be y equals mx plus b. And let me give a better color for that m. It's that m right here, which is the value of our derivative that we are so interested in this chapter. And it's also going to be the value of this limit right here. So the limit of that difference quotient is exactly what gives you the required slope m. That would be the instantaneous rate of change of this graph. If this was, say, time going this way, distance going that way, it would be the instantaneous velocity, the slope right there. Well, how we calculate it? We have to get a secant line next. Let me draw that in color that will pop. And that's where the A, F of A is coming into play. A is going to be a really, really small quantity. We assume that because it says the limit as h goes to 0. But also, It has to go to 0 from either side. H could be positive or it could be negative. When I draw my graph, I'm just going to draw it so it has a positive. But note that A could be positive, H could be positive or negative. So I'll put A plus H right here. We go up and hit the curve somewhere right around this location. And f of A plus H is just slightly higher. So now the line that we have that goes like this, it's not the tangent line. Anyone recall what this was called? Exactly, this one is the secant line. Now imagine you want to calculate the slope of the secant line. That's the one thing we can do. It's impossible to calculate the slope of the tangent line directly by using just that single point. You need 2 points to calculate a slope. But if we're dealing with the secant line, here's how the slope is calculated. We'll go m equals, then we take f at A plus H. That's going to be this top coordinate, subtract f of A. So it's the difference of the y values, the outputs, divide by the difference of the x values, the inputs. We would take A plus H first, then minus A, but that would all simplify in the denominator. It becomes f at A plus H minus f of A, all divided by H. So that's the slope of the secant line. No matter how big or small H is just not allowed to be 0, because if it is, you divide by 0 right exactly there. So H is always non-zero, unfortunately. It means, well, you can't just put a number here and get the exact slope of the tangent line. You have to approximate. Or here's the other idea. Take the limit as H gets smaller and smaller and smaller. That means this blue dot gets closer and closer to overlapping with the other darker blue dot, where the tangent line is based on. We don't care about it obtaining A exactly. We just want to know what happens when it gets closer. What does its value turn into in the limit? And it turns out that right there is exactly what we wanted. That's the slope of the tangent line right at that location. So this equals the slope of the tangent line. And that's kind of how this process works. The limit is not guaranteed to exist. Some functions don't have an actual tangent line at a certain point. But if it does exist, we'll be able to tell right away just from cranking out that limit. Again, that's the major purpose of all that limit machinery we've been doing since really the second day of class. Any questions, folks, before we give this a try and calculate our first derivative? Okay, let's try this out. So we definitely want to add some graph to this so we can just see what's going on. But first, this is what our function looks like right here. It's just y equals x minus 5 divided by x plus 3. Duplicate the definition here just so that we have the formula to look at once again. And the graph of this thing is right here in Desmos. Let me just scroll to this portion for a moment. So there's our curve. We want to find the equation for the tangent line right at 1, -1. So that's going to be right here. Now, if you were to put the graph of that tangent line, would you say it has positive slope or a negative slope? I agree. The tangent line is going to be slanted kind of like this, much like the problem that I drew up above. If the slope is positive, then when we go to do this limit, we better get positive here as well. So at least there's a way to double check if your number is at least in the right field on the number line, positive versus negative or 0. And we'll come back to this once we produce the tangent line equation. So now let's give this a try. We're going to walk through that definition very carefully and calculate first the slope. If we want the equation of the tangent line, we'll do m first. Well, it says we need to take a limit as h goes to 0. We might as well just pen that in right now. Limit as h goes to 0. And it says we're dealing with the f of a plus h minus f of a, all divided by h. Now the question then is, we know h is changing in the limit, getting smaller and smaller, but what is a in our problem? Anyone spotted the a value? Exactly, it's got to be the 1 value. The place I got this a and this a came right here. It's from the point that was provided. So if we go down below, we were provided the point 1, -1, and that tells us in this definition, a equals 1 coming from there. Does that make sense so far? Okay, now that we have that, we just know what's going on right here. It's f at 1 plus h minus f at 1. So let's write that in. F at 1 plus h minus f at 1. And this is a limit, all divided by h. Now, this problem is also a little bit about function notation as well. Just a reminder, when it comes to definitions in these courses, calculus and other math classes, function notation is used a lot. But if you're just writing down an equation for a function, sometimes we don't use function notation. It could be a y equals or s equals and so on. But if you have to go back to the core definition, one thing that's always allowed in function notation is this. Y equals f of x. In other words, that's the f of x function right there that's being used in the definition. So now when we go to the next step, we're going to be plugging 1 plus h here and here and crank out this limit. Essentially, we're done with that definition. That's all what's happening right down here. Any questions at the moment before we start? Okay, so as we go through this limit, these are longer computations, so it's good to go slowly at first. The more methodical you are, the more time you're going to save in the end of the day. First thing I'm going to notice is f at 1 plus h is going to give us a big old fraction, and f of 1 is not going to be so bad. But if I already have a fraction in the numerator of the entire fraction, it might be a good idea to move h out of the way. So what I mean is I'm going to write this as limit. H goes to 0, but 1 over h here, and then put the numerator in those big parentheses, which is always valid. Division by h is the same as multiplying by the reciprocal of h. What you're achieving is it's just a little bit less writing. You won't have a fraction this tall eating up all your white space as you go to write things out. So a slight organization step. Now we go back to the function. I'll highlight that in blue. And for this one, f at 1 plus h, we'll put a 1 plus h where this x is, minus 5. And then 1 plus h where that x is, let me get it there, plus 3. Now, next portion, go minus. We're going to plug in 1 inside here. But if that point was a legitimate point on the graph, it should just be -1. If it wasn't, there's a big problem in the write-up of this example 1. But if you're not sure, I mean, there's no harm in taking the -1, plugging it inside there and just cranking out what we get. Let's maybe just write out in the margin, f of 1. We're plugging 1 minus 5, and then 1 plus 3. That becomes -4 over 4. So yeah, it's -1, as we would be expecting. So you can take some extra time with it and crank it out. But the punchline is that's a freebie. If that's a point on the graph, then f of 1 is just right there. So I'll plug in a -1 in that location. So that's our limit. We've actually seen limits kind of like this one in chapter 2, not exactly the same, but familiar algebraically. All we now need to do is go through the motions, take the limit as h goes to 0. We're going for direct substitution. And the only thing stopping us is this h right here. The minute you eliminate that h algebraically, you can take the limit by direct substitution and your work is done. So in a certain sense, whenever you do this problem, the goal is to cancel this h, the one highlighted in yellow. It also came from the original problem that we wrote in the definition. So cancel h, then use direct substitution. So let's give it a try then. This one's not so bad because when we plugged in 1 plus h and the 1 right here, there's not a lot of variables. It's just the variable h we have to deal with. So maybe first thing, let's maybe simplify that fraction. We'll say it's equal to limit as h goes to 0, 1 over h multiplying with where the red dot is. Let's just call this h minus 4. Down below, we can call it h plus 4. And that's just a glorified plus 1 at this stage. So I'll go plus 1. Give a little bit extra space in the parenthesis because we need to now add up the fractions. That plus 1, we can give it a field promotion. There we go. It's now a fraction, 1 over 1. And all we need to do is put in the missing denominator. I'm not sure why I put parentheses on that. Sorry, that was a distraction. Oftentimes I do need parentheses when I do these, but not this time. I need them over here. We can put h plus 4 here. And here, we now have the common denominator, and we'll add up across the numerators. Does that make sense to folks on the algebra backflips we're doing? Okay, let's continue on. It's now equal to the limit as h goes to 0. Because I'm combining the fractions in those parentheses, we can drop those parentheses and go 1 over h is multiplying 1 overall fraction, not 2 of them. Common denominator is h plus 4. And across the numerator, it's h minus 4 plus h plus 4. So now it's turning into something that we can definitely work with, right? We can cancel the minus 4 and the plus 4. That combines with 2 h's left over, which will allow us to cancel with that h down below. And if you're not too uncomfortable, you could do all of your cancellations right at this stage. But that becomes kind of unreadable, so I'll usually take extra steps for the notes. This is now limit. H goes to 0 of, across the numerator, just 2h. We can multiply our denominators together, combining into one overall fraction as h times h plus 4, then cancel here to here, and we're basically there. Would you folks agree? We eliminated that h, it's just gone. At this stage, you can use direct substitution. Let me show it in one more step to really emphasize it. It's now the limit as h goes to 0 of 2 divided by h plus 4. Now think continuity, that's a rational function. The only non-domain element is -4, so you can just directly substitute 0 for h. And I'll indicate it this way. That h goes to 0 in the limit. It's now done. The whole thing outputs to 2 over 4 for a value of 1/2. So now if we trail back this long line of equalities, what we found is the slope of the equation to that tangent line is exactly positive 1/2. It can't be any other figure. This always has a unique solution. So we're almost there, except we want the full equation. There's just a little bit more to do. I would say this is 90% of the main takeaway for this problem, though. Any questions at all, folks, on getting to that 1/2 here? Okay, checking with the graph. If we go to 1, oh geez, that's hard. If we go to 1, -1, yeah, I would imagine this tangent line, I would have guessed it looks like a slope 1, but I buy 1/2 as well. The scale going that way is not the same as the scale going this way necessarily, so my eyes could be tricked. But I'm very happy it's positive. That was the major thing that I'd be worried if I didn't get. So you could consider that step 1 if you're finding the equation of the tangent line. And step 2 is just a bit of algebra review. Pick your favorite way to build a line. I'm just going to use another color to emphasize this portion. For me, I usually go this route. Y minus y1 equals a slope m times x minus x1. It's not necessarily always the most efficient way. So if you do it a different way, using y equals mx plus b, say, don't change your strategy. If it works for you, then keep on using it. We do go this way. Notice we already have the slope m, so we can just substitute that in right here. When it says x1, we're referring to the positive one, and when it says y1, we're referring to the negative one. So really, everything is provided that we could want. Let me just put here, 1, -1 equals x1, y1, and now we're plugging in information. We'll go y minus the y1 coordinate, which is -1, equals the slope of the tangent line, m. Again, follow those equalities, it came out to 1/2. And if it's helpful for you, you can just relabel it, since that's a lot of equalities. Then down below, it's x minus x1, which is the positive one right here from the original problem. Now, if you stopped right here, I mean, I'm not too worried about that. It's right. The instructions didn't say solve for it or write y a function of x. I still think it's a good idea, and I'll show you why in a moment. If you solve for y, you can just plot that tangent line and see if it actually looks like a tangent line on the graph. So let's take those extra steps and solve for y. This becomes y plus 1 equals 1/2 x minus 1/2. And I'll go to the right. I'm running out of vertical space. The equation for the tangent line is y equals 1/2 x. I have -1/2 minus 2/2, so -3/2. And I'll put this in a box because there's a lot of work on this problem, and that was our end objective. Find that equation there. Any questions at all, folks, before we test this out? Okay, so if we go back to Desmos, here's the moment of truth. It'll be y equals 1/2 x. It definitely looks wrong, but then go -3/2. And that is the picture we're expecting to see. That is the equation of the tangent line. What makes it a tangent line equation is, well, if I zoom in more and more right here, the blue line, which is simple and linear, well approximates the red line, which is a nonlinear curve. What I mean is, keep on zooming in, and if you are nearby +1 for x, there's essentially no difference between the linear tangent line and the nonlinear curve. Well, that's the picture we expect to see if we're getting everything just right. But notice, if you change things even a tiny, tiny bit and say, instead of 1/2, maybe I did some rounding up and got 0.49, just doesn't even look right anymore. This is no longer an equation of a tangent line, and there is no one point you can zoom in that's going to make it look correct. There is always separation except for the intersection point now, if I don't have the exact value right inside there. But that's kind of nice. If you have the equation of the tangent line, then it gave us a couple things. The 1/2 there is what we would call the derivative when x equals that +1 for a. We also produced the entire tangent line all in one shot. Well, we did it, folks. Any questions at the moment on getting through that process? Okay, our goal today is to practice that some more, because if you change the function, this work in the middle is also going to change in a pretty big way too, right? I would say if you go back to section 2.3 and look at all the different kinds of limits that you calculated, that was meant to kind of capture all the scenarios you're going to see here in section 2.7, 2.8 on the types of limits you're going to be encountering. So let's try this out again, but this time let's do it in an application. So here's definition 3, but definition 3 is pretty much, again, the same kind of stuff that we were doing on the first day of class. Figure 5 is directly out of our textbook. And let's walk through these definitions first. If you haven't taken a lot of physics classes, then you may not have talked about the displacement function a lot. But what we mean by displacement is the distance from a starting point. Now, our class isn't too fancy with our physics. If you take Calculus 3, you'll do some more and more interesting things. But for us, we're only tracking motion across a straight line. Think something on a train track, one single dimension. And we're just measuring the displacement from the starting point. We'll refer to the displacement function as simply s, and sometimes we label it as f of t. Kind of like how sometimes we write y equals f of x, and we might give a function as just y, like in the last problem. The function f, or if we call it s, is the position function. And if we want to calculate the average velocity, hey, that was like our first homework question where we approximated it. Well, this is the process. Average velocity is that difference quotient. It becomes this altogether once we simplify the denominator. And it's this picture once again. T is time, S is displacement, directed distance from a starting point. And the average velocity is the slope of that blue line, the secant line there. It's not good enough. We want instantaneous velocity. And all that's missing is a limit right exactly here. So that's kind of the interesting thing about this is when we go to calculate the equation of a tangent line, it feels like it's just a purely mathematical pursuit in a certain sense, but it's not true. A slope can be many, many, many different kinds of things. And this is just a really quick context. If you want instantaneous velocity, or we'll just say velocity altogether, then you need this equation right here. Well, you just need the slope of that equation. And to do that, you just take the limit in front of that difference quotient. That will give you the instantaneous velocity at time t equals a. So that's what we're going to try out to very next. Any questions, folks, before we give it a try? Okay, so this is how we get instantaneous velocity. It's taking a first derivative. Later on, we'll say, well, if we took a first derivative and got a velocity function, that is a function in its own right. And you might wonder, could we do it again? Could we differentiate it? The answer is yes, you would get acceleration. Could do it again, you get something that physicists call jerk. I'm not sure why they call it that, but that's what they call it. We'll leave them alone. And you can keep on taking more and more derivatives. It just gets foggy what the physical intuition might be for them. So we're going to just take this right here. We'll go to example 2. It says, just a really quick context. An object is dropped from the top of a 100-meter high tower. So tracking distance in one dimension. At the original position, where we're 100 meters, that is going to be our initial place. As time moves on and it falls, that'll be our displacement. So if it's falling and going downwards in our frame of reference, we're expecting our velocity to be negative. We're losing height in this kind of situation. So it says that's going to be the governing function. 100, probably coming from the 100-meter high tower, minus 4.9 t squared. The 4.9 is coming from acceleration due to gravity, and we'll look on how to calculate those values, giving initial assumptions about acceleration. Yeah, go ahead.
How do you put the t squared in front?
If I put t squared right here,
Yeah. How do you solve that?
go like that, you're saying. I would do it the same way I'm about to do this one. It would just be a harder problem is all. I would put it inside this limit right here and just work through those same kind of steps.
Yeah, because the other question, so we want fraction of t squared. And then that's it. Over.
Gotcha. Let me take a look at that so I can see if I can remind myself. This was 2.7. And oh, this one right here. Yeah, it's going to be done essentially the same kind of way. So instead of substituting values in, oh, that was a little too far. Instead of substituting values into that t squared right there, all your work is going to just throw it, your f of a plus h, your f of a, it's just going to go right down there in the denominator instead. So you'd have, let me actually put the first steps on this. For this problem number 13, we would say v at a is limit as h goes to 0, f at a plus h minus f of a all over h. So that'd be our first step on that. Then it'd be equal to the limit h goes to 0. And I'm going to do the same trick that we did before. If we have a fraction in the numerator, I'm just going to pull away that h, make it multiplication by the reciprocal, 1 over h. And now f at a plus h, we just put an a plus h right here, 1 over a plus h squared, then minus 1 over a squared for f of a, and that's your new limit. Similar to the one that we did at the start of class today, or example 1. But does that make sense for getting going with that problem there? Oh, so it's from the f of a right here. When we plugged in a, the t itself swaps to an a in that one. It's a little bit weird, right? Because on the first one, we plugged in the number 1 and got a number out. But they're asking us to do it at time is a first to start off. So it looks a little bit weird to begin with. Does that make sense at the moment? Awesome. I'm going to take this as a screenshot. And if you want to come back to this for homework assignment number 2, it's going to be posted. Let's put it maybe just right under example 2. I think that'd be a good location. Okay, well, let's try it out now for this one. In this equation of motion, it says, what is the instantaneous velocity of the object at time t equals a? That's one limit. We'll do it again when time is 1 second and then when time is 2 seconds. And when they say instantaneous velocity, let's remind ourselves, we're just talking about that function right there. So let's begin by calculating velocity at time a. A is arbitrary this time, but the good news is, if you can do it at time a, where a is any valid time, you're going to get an answer that involves a, but then you can just swap in values for a. We'll plug in 1 to calculate that limit instantly, and same with plugging in 2. So it's like we're getting a formula for the velocity, the derivative of that function. So let's start off by saying this is equal to limit h goes to 0, f at a plus h minus f of a, all divided by h. Now, on the first problem, we knew the point we were going at was 1, negative 1. So we just said a is 1, and we plugged 1 right here and right here. You might say, why don't we do that right now? Plug 1 there, and similarly with 2. Well, that's because we would be doing essentially 3 problems. We can do it with a variable a. The rest of the work just falls right into our lap. So essentially what we're creating is a whole new function. We're not going from the number first, like on the last problem. Any questions then, folks, before we run through this limit? Okay, first step, definitely write down this equation right here. It really will help with aiding in memorization. Next step, even if this f of t is gone, we assume the function is 100 minus 4.9 t squared. But if it's written in, I guess that's definitely helpful. It makes it a little bit more clear. We have limit h goes to 0. I'll just make one big fraction bar, keep h below, since we don't have a complex fraction. And let me work on, in a different color, this portion first, f at a plus h. We'll plug a plus h there, and this is what we're going to get. It will be 100 minus 4.9 a plus h squared. And that's it. That's our full evaluation there. Then across minus, we need to copy an f of a. We have to be super careful with parentheses because the function involves 2 terms, not just 1. And f of a, I mean, that looks weird in a certain sense, right? Function here, we will just turn into an a squared. So 100 minus 4.9 a squared. Well, that's not too terrible of a limit. We just need to expand this out, combine the like terms coming from here. But remember the objective in every one of these problems for calculating a derivative, even if we call it instantaneous velocity, that h has to cancel some way, somehow. So there's always kind of like a built-in check on this. If algebraically I cannot cancel h, there's probably some small mistake on the earlier work. So let's start expanding things out and see what falls out. Limit as h goes to 0. And now I'll put the red dot in where I'm at. I'm just copying for the moment. 100 minus 4.9. We need to expand a plus h squared to get a squared plus 2ah plus h squared. Here, we could just distribute through the negative sign if we'd like and get minus 100 plus 4.9 a squared. And then the whole thing is being divided by h. Any questions at the moment so far, folks? Okay, same kind of things we've done before, but the algebra can get a little bit hairy. Next thing we can do is, let's just go for the cancellations we see right now. Those are gone. Now I have a 4.9 a squared. I'll cancel with this, but I really ought to distribute first before I cancel. Otherwise, it looks kind of crazy. So my next step, it's limit, h goes to 0. I'm distributing in that negative 4.9. So negative 4.9 a squared. 2 by negative 4.9 is negative 9.8. Let's see. Yeah, negative 9.8. That look all right to folks? Awesome. Arithmetic is tough when you get tired, so that's one of the hardest first things that goes. Negative 9.8 ah minus 4.9 h squared. We've already canceled that 100, so I'll copy plus 4.9 a squared. Down below, still that h that we must eliminate. But how can we eliminate h? The way h eliminates is any term that doesn't involve h as a factor in the numerator, like say this one, it had better be gone or else we can't cancel h. But good news, this one and this one are opposites. They are gone. They're canceling immediately. There's two styles for canceling in the numerator here with what's left over. It's always going to be up to your choice. Some people do it this way. They'll just go gone, gone, power 1. If you like that, I'd say you don't have to change, keep on doing it. For me, it's kind of confusing because I can't tell what I did in this one step. So I'm usually going to do it in this way. I'm a fan of factoring, so I'm going to factor h out of the numerator. But the punchline is, whichever way you're used to doing it, you don't have to change. Just keep on doing it the same way. Limit h goes to 0. We factor out 1 power of h. There'll be negative 9.8 a minus 4.9 h, multiplying that factor out. Then over here, we have just h. Now, these cancel, and it's a little bit more clean to see how they cancel. And that was our objective. It doesn't mean the problem is done, but it means we can use direct substitution, our major goal to evaluate the limit. So last step, we're taking the limit as h gets smaller and smaller and smaller of negative 9.8a minus 4.9 h. But if h is going to 0 in this limit, so is that. Negative 4.9 h is effectively just gone. And the whole thing settles at negative 9.8 a. That's our instantaneous velocity right there. We might as well highlight it, make it look special. And one thing I forgot to read was that it has units, right? Anyone happen to know what the units should be for this? Exactly. This would be in units of meters per second. All right, m/s to emphasize that. The reason for meters per second, well, is s right here is in meters. And that means everything in the numerator of that is also in meters. So that has units, meters. But what about the denominator? There's an h there, and h is always kind of confusing. But if we scroll up and look at the graphics, it says where h came from. H is right here, a tiny offset on a, so that we could get a secant line and take a limit on its slope. But that means it came from the time variable here, and I believe time was in seconds for this problem. So that means the denominator unit is seconds. Units, seconds. So every time you do this difference quotient, take a look at what the unit is for the original function, the unit for the variable, and you will form a quotient like this one, meters per second. So the instantaneous velocity at time a, where a is arbitrary, is exactly that figure down there. Any questions at all, folks, on running through this so far? Awesome. So we did one limit. I'm going to just temporarily circle that to remind myself, but there's 2 more limits we have to go through. And it feels like a slog, right? But like we mentioned, if you can do it once with an arbitrary variable, call it a, call it x, it's really up to a matter of stylistic choice. Then you can plug in values for that variable and evaluate the velocity multiple times. So let's plug in time 1. I would write for this. Velocity at time 1 equals, go to our velocity function, and we're just replacing 1 for a. It'd be negative 9.8 times 1 for a negative 9.8 meters per second. Then if we do it at time 2, it's the same kind of spiel. Velocity at 2 seconds. We'll go back to this function here. Let's see, plug in a 2. And that should be something like, oh geez, 19.6. Awesome, thank you for the help on that. Meters per second. Oh, thanks for the negative sign. Negative 19.6 meters per second. And that might make sense, right? If you're dropping an object from 100 meters up at 1 second, it's going pretty fast, negative 9.8 meters per second. But after 2 seconds, acceleration due to gravity is also pushing it down faster. It's going negative 19.6 meters per second at time is 2 seconds. Eventually it's going to smash into the ground, but that's kind of interesting to see all these weird limit movements or limit methods working together with some arbitrary function. It seems to match our intuition of what should happen. Any questions at all, folks, on finishing off this here? Yeah, go ahead.
You're done equations and taking weight to calculate terminal velocity. You're done equations like those, they're huge.
For terminal velocity, I haven't done too many, but they're not too bad to start, but they can get very gnarly once you start taking into shapes, the drag, and all sorts of extra assumptions. But yeah, you could calculate terminal velocity and say, it's usually like a first set of problems in differential equations. And they do get into that kind of stuff as well. Other questions about that so far? Awesome. This one, we could do terminal velocity, but we'd have to change some assumptions, right? The tower should be a little bit more than 100 meters. And we'd have to see just what happens to the velocity of this as time increases more and more and more. We really would just be taking a new kind of limit altogether. But so far, really the purpose of this problem is we're taking derivatives, what are they good for? And this is one really fast, nice application. We'll see many, many different kinds as well, particularly in chapter 3 and 4. Well, I think we have time for one more gnarly kind of problem. Any last questions or comments before we try another? Terminal velocity is when you have an object, say like a skydiver who's falling through the sky, his speed is always increasing, but up to a point. There's a limit at which that person is going as fast or plummeting as fast as they ever will. That's their terminal velocity. So it's like the maximum speed we expect them to fall. Other questions so far? Yeah. Like right here? Yeah, absolutely. Yeah, absolutely. So first, let's take a look at breaking down this. I'll be happy to show how it goes if we say plug in time is 1, for example. Is that what you're asking about as well? Gotcha. So first, if we're doing it at A, and we need to come up with this right here, let me highlight these a little bit better. Let me go purple on this one. If you want to put this together, it's not a bad strategy just to go say to the right margin of your paper, calculate f at A plus h. When we go to calculate that quantity, we go back to the f function that's right up here and just start copying it out to begin with. There'll be 100 minus 4.9. And here's where we make a substitution. Wherever the t is in that function, we put in the input a plus h. So all of that right here just gets dropped into that location where it's highlighted in green. Does that make sense on that step there?
Yeah.
Awesome. Then the weird step is we have to put minus to line them up. And this portion, this is f at, or A, let me try again. It looks really weird because you're just going back here. The function goes 100 minus 4.9. And where this t occurs, we are just going to swap it to a new variable a. it becomes a squared. Then all that just gets dropped down right inside here. From here out, I drop the color coding and we're just cranking out the limit. But does that make sense on how they kind of go together to start it off? Exactly. In fact, you could have done this whole thing and called a T, and that would have been just fine, really. That's what they're going to be doing in the next chapter, chapter 8. Yeah, go ahead. Oh, the parentheses around here. Oh, maybe first start with this one right here. I had to have the parentheses in this location because order of operations says I have to do exponentiation first, and then the multiplication of negative 4.9. So those parentheses were to help me out just with that process. But these parentheses by that red dot are actually a little bit different. These parentheses are only because there's a negative sign right here, so I had to match it up. And because the function came with 2 terms. It means the negative sign has to distribute to this location and to that location as well. And putting in those parentheses just reminds me to flip both signs and get an actual positive right here. That makes sense for that one? Gotcha. Now let's return to the question that you were asking before. This is definitely a harder question, right? We're doing a limit at a specific number. But if we had tackled, say, at time 1, here's what that process would look like. It's kind of like how example 1 went. Let me first copy here so I just remind myself what the function looks like. Now let's try it down below right here. So focusing at time 1, suppose we went directly for instantaneous velocity and calculated velocity at time 1. We'll still take the limit as h goes to 0. The function is still going to be f at a plus h minus f of a divided by h. And now at this stage, we are going to start plugging in values this time. When it says t is 1 right here, we're going to go and set a equal to 1 second. So that will make a replacement right here and right here all together. And you know what? Let's actually maybe work things off to the side. There's a kind of 2 schools of thoughts when it comes to these long computations. Some people like to put it all just one big line, color code things to see what's what. Or you can separate out things in the margin and then plug them in once you're all set. Let's use the margin strategy and do f at a plus h first. It turns into f at 1 plus h. We'll go back to the function, and we're going to plug 1 plus h right where it's highlighted in green. So it turns into 100 minus 4.9, 1 plus h squared. Now we're just going to simplify it right here and now. It's 100 minus 4.9. 1 plus h squared, when we expand, becomes 1 plus 2h plus h squared. And we're just about there. The result is 100. I'm distributing in the negative 4.9 at this step to get minus 4.9, then minus 9.8h, minus 4.9h squared. Should have given myself a little bit more space right there. All of that goes into this location. So let's plug it in. This now turns into the limit as h gets smaller and smaller, heading towards 0 of 100 minus 4.9. I guess we could combine those right now, couldn't we? Well, let me actually put it in just so we know where it came from without changing it. 4.9 minus 9.8 minus 4. Oh, I forgot something. Minus 9.8 h minus 4.9 h squared. Okay, one part done. Now let's return to, I forget that erases everything. Let's return to this part, f of a. Now it doesn't want to erase, it's really picky. Maybe we'll just go this way. There we go. Oh, that doesn't work either, does it? One last try. Let's go for I'll do it in yellow. That always is a friendly highlight color. So now for f of a, well, if we're doing at time 1, we set a equals to 1. So we're doing f at time 1. And this one's not so bad. There's no variable this time, making it nice. 1 is going to go right where the t is. So it becomes first 100 minus 4.9 times 1 squared. That means it's just 100 minus 4.9 altogether. So back over here, I need to copy that negative sign to start. F of a turned into f of 1, and it's now this quantity. Oh, and I need to be careful once again. That's an easy step to miss. It comes in as 2 terms, so I need parentheses to allow the negative sign to distribute. 100 minus 4.9. Then finally, whole thing, all of which is divided by h. Let me highlight that in yellow just to show where that quantity came from. So when we plug in the number, this is where we settle. And now we're really close to done with this one. Any questions so far, folks, to that stage? Okay, you know what's kind of weird about some of the math you do in a calculus class is it just feels different. I'm looking at this and I'm thinking there's no value in me subtracting 4.9 from 100 because this is going to cancel it immediately. 100 minus 4.9, take it away. 100 minus 4.9 means that is an instant cancellation. Does that make sense to folks visualizing it that way though? It's definitely weird, right? I can't think of an algebra class where I would have done that, but in calculus, that's considered normal. Now with what's left, it only involves h. I'll factor it out. Lim h goes to 0. H factored out leaves negative 9.8 minus a 4.9h. Still, all of it is divided by h alone. Now we're in the right position for a cancellation. Those h's are gone. As h goes to 0, that portion's gone. You can cancel it right here, but I'll show the extra step. Lim h goes to 0 of negative 9.8 minus 4.9h. In the limit where we can now use direct substitution, that converges to 0, and we get an overall answer of negative 9.8 meters per second for the equation of motion. So that's finally our instantaneous velocity at exactly time equals 1 right there. Doing a time equals 2, kind of the same sort of thing. But let's double check our answer at time 1. Hey, we got it, negative 9.8 meters per second. Well, any questions, folks, seeing it either way, this way or using just the variable?
Where you whatever did it always go after
Yeah, absolutely. So if this was, say, a cubic, we would add 1 plus h cubed right there in that location.
so it's like a plus next one.
It'd be, say, a plus h, but then all raised to that exponent. Yeah, exactly. Other questions at the moment? Okay, well, these have been some kind of weird limits. At least they have context, right? That definitely helps. And with what I have on the notes so far, I believe I have just one more limit. Let's see, this one's a quadratic, so this one shouldn't take too long to get through. How about one limit and just a quick slope to call it a night? That sound all right to folks? Awesome, let's give it a try. So now we have another one of those weird situations. They're not asking us for, say, the derivative at 1. We want it at a. But also notice what's new here. We have our ordinary difference quotient formula that I'll reproduce here. But this theorem is just a geometric reminder. Think of it as a big reminder that will influence us in chapter 3, 4, 5, and 6. It just keeps coming back. It says the tangent line to y equals f of x at a point a f of a is a line through a f of a whose slope is equal to f prime of a, which we will call the derivative of f at a. A suggesting function notation, which is appropriate. The derivative is just a brand new function from the original one. We say we derive it from the original function. That's part of why it gets its interesting name. So from this function right here, when you see f prime at a, we're calculating the derivative, but the disservice the theorem does here is it doesn't tell us the formula. What I would suggest doing is each time you go to calculate the derivative by the definition, it's a good idea to just write it out. That way it's just going to invade your subconscious. You can't help but remember it after a point. So here's our derivative, f prime at a. But never forget, all the interesting things in calculus comes from a limit, which is really weird. Here's the one for the derivative. Always limit as h goes to 0 of f of x plus h minus f of x divided by h. So that's the quantity we need to calculate. Like before, let's break this down. I'll first work out f at x plus h. Let's do it on the right-hand side. Next, we'll do f of x and then work from there. So f at x plus h. Really, it's just a bunch of algebra, but it's kind of tedious algebra we have to be careful with. Because this time, if we drop a sign or we write a 3 when it should have been a 2, there's no way h is canceling. We're just stuck. So we have to be very, very precise with our algebra at this stage. So I'll write, going back to the function, if it starts with x squared, we'll have x plus h in place of that x squared. For the negative 5 times x, we'll go negative 5. But we don't have x. We have x plus h that goes into these parentheses. And the last part is plus 7. So we need to expand out all of this stuff. We'll get, when we expand the perfect square, x plus h squared plus 2xh plus h squared. So that navigates us through this location here, just foiling it out. On this one, distribute through negative 5, and we get minus 5x minus 5h, and then plus 7. Now notice there is not a single like term here. We just have to deal with 1, 2, 3, 4, 5, 6 different terms. It is what it is. That's okay. Let's move over to this function. Minus f of x. Oh, and I noticed I did make a mistake there. I was meant to calculate f prime at a. I put in an x here and here, but that is okay. Whether you say a or x is completely immaterial. So to emphasize that, let's put an x here as well. We will be doing that in the very next section. And so when I take homework on this homework set, it's kind of a toss up whether you used x or whether you used a. If you do decide to use x, it's good to be consistent though. So if I started with a, I should have used a here and here. Is that all right with folks if we keep it with x? Okay, that helps us out. That's a less rewriting over here for sure. Now let's go to the f of x. This one is always weird to me, but there it is. They gave us f of x. We're just literally dropping it in. And because we chose x, we're not even changing the variable this time. That's the full format. We just need to plug in our results and crank out the limit. Any questions first before we plug these things in? Okay, so for our next step, this will be the limit as h goes to 0. I'll put in the numerator first. F at x plus h, when we expanded it out, gave us this mess. X squared plus 2xh plus h squared minus 5x minus 5h plus 7. So we got that so far. Then match up the minus sign. It's easy for me to forget that thing. And also if f of x comes in multiple terms, 3 this time, the parenthesis here is absolutely vital. Now we're copying f of x, which is x squared minus 5x plus 7. So we can close off the parenthesis, divide by h, and we're well on our way. Just one real big mess of algebra, but the good news is there's loads of cancellations. Now, if you're feeling like you're trying to save some steps writing, I'd understand this is a lot of writing. You have negative x squared canceling with positive. This is positive 5x after distribution, canceling with a negative. But to me, that's confusing, so I'll show the extra step of distributing the negative sign through. So this is equal to limit h goes to 0. I'm going to just copy all this stuff to that point and then distribute. So x squared plus 2xh plus h squared And for me, it's easy to make a mistake just by forgetting to copy something. So be meticulous, be methodical, and it saves you loads of time. Minus 5x minus 5h plus 7. If I drop something, let me know, or else we'll never get through this one. Now distribute the negative sign will give you negative x squared, positive 5x, minus 7. All of which divide by h. Now, honestly and truly, a lot of what we're writing here, it's more about really accounting, note-taking, and just being meticulous that nothing was left out. The better you can organize it, the cleaner you can write it, it really helps with accuracy. So now, remember, we have to cancel that h, which means that x squared has to be eliminated. And there's its opposite term. Now 2xh, it can or might not have a like term. We're not worried because if it has h, we can still simplify without canceling it. Same with h squared, that one's okay. But this negative 5x cancels here. And a positive 7 finally cancels way out here. Now, you could cancel your h's here if you'd like. I'll write out this extra step. All that's left is limit h goes to 0. I'm going to factor out h from the surviving terms to get h times 2x. Factoring out here just drops the power by 1, so plus h. Here it eliminates it, so minus 5. All of which is still divided by h. And here's our hopeful cancellation. If you canceled here and here, it doesn't mean 100% you got the right thing, but it means you have overwhelmingly strong numerical evidence you did everything right. Otherwise, you made two specific mistakes that canceled each other out to allow this to work. So that's extremely rare. It tells us we're probably on the right track. And now, well, this is the limit. As h goes to 0 of 2x plus h minus 5. But h is going to 0 in the limit, so that's just gone. And we get 2x minus 5. That means this one's completely done. Any questions or comments so far, folks? Okay, this is hard, and we're going to take lots of derivatives in chapter 3. I want to give you a kind of a preview of just what's happening with these derivatives. Take a look at the answer, 2x plus 5, and the original function. Kind of what happened is this 2 went down, gave us a 2x. The power 5 went, or excuse me, the x here just went away, so you get negative 5. And the constant went away. There are strange little tricks with the original function that's going to allow us to calculate this derivative in about 2 seconds. We just have to get familiar with them. But for the moment, because we're just learning this kind of stuff, and because this limit is still valuable even when we have the shortcuts, the exercises in this section say calculate using the definition of the derivative. And what I mean by that is really going through these steps right here. If you know other information on how to calculate the derivative, you do have some shortcuts to know if your answer is right or not. But this is the work that's expected on these problems. And I want to say that's kind of unusual. Usually when I write a problem that's going to appear on exam, I'm not too worried about the method, but this is the one exception where knowing how this method works is really the thrust of the whole question. Then later on, we'll just calculate derivatives the fastest way possible. Other questions or comments, folks, at the moment? Okay, well, now it asks us a follow-up question. This is just a reminder that anytime you calculate a derivative, even if you put in a variable x, you are finding the slope to the tangent line at a point x, f of x. And part B is asking, what is the slope of the tangent line to y equals f of x? We mean the same f of x function at the point 0, 7. It would be m because they're asking for a slope. But if they're asking for a slope, they're also wanting a derivative. We indicate it with an f. And this is the prime symbol. It's not a power. Try to avoid writing it this way. That would have a different meaning. Try to give it a good angle. And if I say f prime, that's what I'm meaning. F, and then that's the prime. We're doing f prime at something. You can see what number has to go in to get the right derivative. Close, it wouldn't be 7 on this one. It'd be the 0, yes. So think first coordinate, that 0 goes right exactly here. So if we calculate f prime at 0, that will be the right specific slope to the tangent line. Following these equalities, this is f prime at any x. So we're literally going to that derivative, that result, and saying 2, move that red dot, times 0 minus 5 is immediately the slope to the tangent line. We will get a -5, and then it's completely done. It's in that sense that this is really a brand new function. We really have an infinite amount of work in a certain sense. Change the point, maybe it's 1 something else. Just plug the 1 in there, and there's a new tangent line with a brand new slope that you're getting. So this derivative, 2x minus 5, encodes all the information for all of the slopes of every tangent line you can put on the graph. Kind of weird, but it's just a brand new function is another way to think of it. Well, I think this is a good stopping point for us. Any last questions, folks, about any of this kind of stuff? Okay, it's a big concept. It's a wild topic. So if it feels kind of foggy still, keep in mind, when we come back Wednesday next class, we'll be in section 2.8, but we're still doing this. It's still crank out these kinds of derivatives, just more practice. Well, have a great holiday, folks, and I'll see you all later. Yeah, go ahead. It doesn't make it too much more complicated. It's definitely more practice, I'd say. I'd say the worst thing that can happen is some of the algebra in the middle might be a little bit more, but same exact formulas.
Quick question.
Sure.
This is on question 18. I don't know if I did this right. I mean, this isn't negative, but
Oh, so this is when we're taking a limit, like going to infinity or
yeah,
something like
or
that?
would this
Gotcha.
just be going? Because I put it in jet. Yeah. Because I got -3. I don't know if this is right, if I did my math right.
I like -3 because if you look at the leading coefficient here in the
Mhm.
denominator, it's -2. So we should have a -2 below. The leading coefficient here is 6. So we
Right.
should have 6 above.
Right.
As far as the author method goes, you pick the biggest power of the variable t in the denominator, t squared, and everything gets divided by it. So that looks good. Let me check. You should be getting a 6. Here, this should be 1 over t. This would be 5 over t squared. This would be 9 over t squared, and this would just be a -2. Yeah, that looks good.
Okay, good.
The only thing that's missing is just the limit as the t
Oh.
goes to infinity here and here.
Yeah, this is my scratchbook. If I
Oh,
don't-
yeah, if it's
Yeah.
patchwork, no worries about that. Yeah,
Yeah. Okay, thank you.
yeah, you bet.
Then we start integrals and,
Yeah, that's another thing that's wild is when we're doing derivatives, it's slopes, but when we're doing,
So tedious. I was looking,
Yeah.
I was like, girl,
when we do
I got work.
integrals, it's areas, and
right,
they are opposite to each other's in a calculus sense.
right, isn't it integral just like area in the line in the graph, something like that, or area in the slope in the graph?
Yeah, and what's wild about that is if you want to find the area under this graph, A and B, the graph might look like this. Suppose you want that area, you'll say area equals f of B minus f of A. That's y equals f of x. And the uppercase f is something that does this. The derivative of my uppercase f is lowercase. That is the most wildest thing imaginable because it's telling you this area depends on nothing but the boundary points B and A and some other function who you differentiate and get the original curve back. Just seems completely wrong even, but it's, yeah, that's what we're getting into.
Isaac Newton was one of the founders of calculus, right?
Isaac and the co-founder was Leibniz in Germany. Yeah,
Can you imagine being their addict, just like critically thinking about math so we can see some clues?
yeah, that's
It's
really
so
wild
cool.
because they're so isolated, right?
Right.
They are kind of working in a box and they're not
Right.
necessarily sure if they're on a mad goose chase or not.
Took a lot of trial and error too.
Oh, yeah,
Whenever
yeah.
you use your theorems, like whatever theorem, like the one we did yesterday, cancel out to 0 and everything all like that. Whenever like this happened, it just blows my mind that someone has gone through and done the math with literally a giant range of numbers to confirm that this is like a fact, it's a theorem. Every time
Mhm.
you just get the shortcut, it's like, I'm going to prove that theory. I'm sure the math behind it was ridiculous. It's
Yeah.
so cool. It's just really well fleshed out calculus.
It is, absolutely. Yeah, they did a lot of good work with the Riemann guy and let's see who else. Bunch of those kind of
He was the guy
people.
that refined calculus, right? Came from like the Baghdad House of Wisdom or whatever.
Yeah.
Yeah.
When Newton and Leibniz first discussed this kind of stuff, derivatives and areas, they didn't have the proof machinery. And so
Right.
some of the work they did was wrong. I mean, there's exceptions to their results. And it was the Riemanns and the other guys that came and made it precise finally.
Right.
I mean, most of the math is through trial and error and proven through time.
Yeah.
There's a lot of things that probably could be now could actually be technically wrong or find a better method that is altogether better.
Sure, yeah.
We already found calculus.
What was that?
You
Sorry.
think already know what we found calculus would be better methods?
Depends.
I don't know. It's really cool.
So,
Yeah, absolutely is, yeah.
And calculus, the entire objective before was just that they were trying to find, they were just trying to find some good point, on a curve.
Yeah,
That was really difficult, and the entire argument was that if you cut up enough, basically cut up in tiny rectangles, and you calculate small distance between those.
now you're thinking
we can
limits,
get to it
exactly.
right. We get to the point where numbers just start to blue, and that's when we know we found correctly at that point. That was the entire argument behind it, right, when it first started?
Pretty much, yeah. There's
It's
other
so
interesting
weird.
things like, some, they're back in the day, like
Uh-huh.
Isaac Newton's time. If you knew a speck of math and you can make a prediction like, I don't know, Mars is gonna be visible on the eastern sky on April 12th. If you can make that prediction, monarchs, like actual monarchy,
what they would
would
imagine.
pay you in gold, they would move you to their palace and they'd just have you spitting out predictions like that.
Oh, it's so.
So that's one of the things
Because-
Isaac Newton did was
Right.
he found the equations of motions of the planets. He found out they were ellipses, not circles, and suddenly he's cranking out all these predictions and people are just losing their mind on how is he doing it?
They think it's magic, but
Yeah.
really it's not.
Not
It's more
really,
like,
yeah.
it's like, can you tell us within the riddle, like, hang on, let me give you a calculation of how far you want to fire this.
Right, right.
I just can't imagine, that powerful brain to sit down and just do pondering. and
Me neither, yeah.
calculations.
So-
So awesome.
So.
I
the-
don't have
the
that kind of brain
suspected-
either.
So the suspected thing for these people to be able to do this.
Uh-huh.
So a genius in our current area is how we classify them is have an IQ 145.
Mhm.
Anything higher than that is classified as a genius. I'm 144 actually. I'm just under that, which is actually this sad. Well, it's mostly because of my English that's held me back, but English is English. I don't really get it. But most people theorize, most of these people had an IQ at least 180 to 200 to even think of this stuff.
Which is so incredible. It is incredibly awesome.
Yeah.
Which is why a lot of people think, like how smart you are is mostly genetic and your environment.
Right.
So genetics can carry you a good ways, so judging from how they are, they probably had a very specific